This is the Computation Center at MIT, which serves more than 40 New England colleges and universities. The heart of the center is this IBM 7090 high-speed, general-purpose digital computer. In addition to the routine work which takes place here, experimentation is underway to develop a new technique of computer usage called time-sharing. At consoles like this one, located in laboratories and offices throughout New England, hundreds of people will one day be able to use tomorrow's computer simultaneously. This man has been using the computer to solve a relatively simple mathematical problem. And while he thinks about what he wants to do next, the computer is busy working on someone else's problem. In this way, scientists hope to break one of the major bottlenecks in the use of computers. Hello, I'm John Fitch, MIT science reporter. I guess most of us are aware of the fact that the computer has come to play an increasingly important role in our everyday lives. It processes the checks that we write, it handles our payrolls, and it even keeps track of the availability of airline reservations. But in addition to solving our problems, which revolve around the relationship between the man and his machine. I'd like to have you meet Dr. Fernando J. Corbato, who's the Associate Director of this center. Dr. Corbato, maybe you can tell us about some of these problems to put this whole business in perspective for us.
Well, to do that, we have to go back about a decade, about the early 1950s, when the real problem was to try and put together computers of this size and speed.
Well, just to get computers to work.
That's right. They're pretty unreliable in the beginning, and they had to be, or people were afraid they'd be unreliable. They managed to lick all those problems. By about the middle 1950s, they were being used very heavily already.
So what would have been the next problem?
Well, the next problem was that of communicating with the computer. The computer basically only understands numbers. I mean, you put numbers into it and these represent something. Well, the next major improvement was in the language that one talked to the computer with.
You could teach the computer to understand English?
Well, no, but we can actually put a particular synthetic language, which is largely technical and which is, to some extent, Algebra 2. And this jargon, which is understandable to a person, is much easier to work with than numbers.
Oh, I see. So once you're able to talk to the computer, then what next?
Well, the next major problem is that of the ability to interact with the computer. The man-machine interaction is very poor. Now, this largely stems from a problem of the fact that we must put only one problem in the computer at a time, fundamentally. Now, in the process of trying to put one problem in the computer at a time, in the early days, we wasted a lot of time putting in each problem and taking him out and then bringing in the next man.
And these computers cost a lot of money.
Yes, indeed, they do. They're between $300 and $600 an hour.
So you don't want to waste time.
No, we don't want to waste time. So we, as most other centers, have resorted to a procedure of batch processing.
What is that?
Well, we combine a great many people who want to submit a job to the computer on a single input magnetic tape. Now, these magnetic tapes are made using computers such as this one here, and they're pre-recorded, and they're taken to the main computer and used as an input tape to the main computer.
Oh, I see. So you solve everybody's problem in turn.
Well, in a batch. A group of people like catching a bus. And the computer calculates this batch through and produces an output tape, and then the output tape is brought over to the computer, and the results are printed out. Well, as you might imagine, this takes a few hours to get anything through the computer at all.
So that raises more problems.
That raises a lot of problems, and people are very frustrated with this type of interaction.
So what do you plan to do?
Well, what we are trying to develop is a new scheme of using the computer, which we call time-sharing, which consists of attaching a large number of consoles to the central computer. It's a little noisy out here. I think it would be a lot easier if I could explain to you in my office how to use one of these where I have one remotely attached.
Good. The idea, I gather, then, is to allow a whole lot of different people to use the computer all at the same time.
That's right. And this is one of the consoles they might be using in the future.
It looks very much like just a regular typewriter, electric typewriter.
Well, that's right. That's what it really is. It's a small amount of electronics in the bottom, and it's attached to the computer. That's the real distinction.
So you might have one here in this office, and I might have one, say, in my office, and there might be one in some university, something like that?
That's our hope. We think that can be done.
How many might you have altogether?
Well, at the moment, we're just working with, at the very moment, 5. In a few weeks, we should be up to about 20. And ultimately, we hope to see hundreds, but we'll probably have to have a better computer before that is.
But I still don't understand now how all of these can be using the computer at the same time.
Well, to really explain that, I have to backtrack a bit and just talk about a little bit about how a computer really works. Okay?
Sure.
So, let me show you. Here at the blackboard. First of all, let me explain just for a moment what a program is, and how a computer really works. The computer's organized around a large set of pigeonholes, which is really called the memory usually. In each memory, the memory consists of these various cells, or pigeonholes, which I can put a number into. Now, the computer, say, has particular numbers in each cell, and it's very hard to read this way, of course, but some of the numbers represent instructions, and some of the numbers represent data. And the person who prepares these instructions and data is the one who keeps it straight what they are.
I see. Those numbers might not mean numbers as such. They might mean to add something in one pigeonhole to something else in something other pigeonhole.
That's right. Some of them are instructions, some of them are data. Now, the real computer, in the sense that the device that does the computation, is a central processing unit which has the calculating parts, and this is usually called CPU.
That's where the work is actually done.
That's right. This is the device that really does the work. And it is able to operate on one instruction at a time. And the arrangement is that it does first one instruction, then the next instruction, whatever that one might be, and keeps doing instructions, and then some of the instructions cause the program to go back in a loop. Now, this collection of instructions, as I just said, is called a program. And they do a particular job and somebody has to prepare them in advance.
How do you get it into this memory?
Well, normally one is read it in from punch cards or something of this sort. And this comes back to the problem of how do you use a computer. And in the past, what we used to do is we have a computer, a 7090 for example, and we used to read them in by cards, but then we got a little more worried about efficiency, and so we now read them in from magnetic tape, which has been pre-recorded. Now, this calculates inside the computer, and it's just one problem at a time, remember. That's the problem. And after several minutes, the output results are accumulated on magnetic tape, and they're taken over to another computer and printed later. Now, this is the older batch processing technique.
One problem at a time.
One problem at a time. And it's pretty clumsy because of the weak interaction between the man and the machine. Now, what we're trying to do is superimpose on this a set of parallel consoles, which are not all near the computer, in fact. In fact, most of them are remote, and let the users use these with a reaction time of a few seconds rather than a few hours. It takes a few hours to get through this path because of the batching and queuing, and it takes, we're hoping, and we're actually able to do at the moment, a few seconds. We'd like to get it down to a fraction of a second eventually. Most of these are typewriter consoles, much like we saw, and we actually are getting to 21 consoles. Eventually, we'd like to see graphical display on this kind of a console. There are technical problems still, but as an experiment to try out some of these more elaborate advanced ideas, we actually are trying to tie two small computers to this one. We have one, a PDP-1 computer of the DEC Corporation, and we have also a 1620 computer of the IBM Corporation. These are more experiments which are a little too advanced to explain today.
Well, I can see now what you'd like to do, but I don't see how you do it.
Okay, well, I have to go back then a little bit more. Let me come back here to the same drawing of the memory and the processor. And which can only work on be at one place at a time. Now let me redraw this a bit. What we have is we actually have one master program, which I'll call a supervisor. And this is the program that is going to run everything. And normally this computer, when it's in the time-sharing mode, is operating a program in the supervisor. We also have a program for each of the typewriter users, say U1, U2, U3, U4, and so forth.
They might not be the same size as you've indicated.
No, they're not all the same size. That's quite right. That's what I meant to try and convey. But, now, the consoles have to type in to the computer, and they type into the supervisor and back out. So the messages are handled by the supervisor for each of the programs. Now, the supervisor is going to relay these messages to the particular programs as they are, and keep track of which user's talking to which typewriter, of course, and so forth. And this would be straightforward enough, except that quite often we'll get more programs than we have room for.
Yes.
So we have a problem, and what we have here is another device called a magnetic disk memory, which I can illustrate this way, of course, just schematically.
It's a big whirling disc on which you can put
that's what I meant to
a whole lot of tape.
Right. Well, it's a magnetic material, much like magnetic tape, on the disc, and it uses essentially a comb of reading heads to read material off the tracks, like a phonograph, pretty much.
I see.
It has a very large capacity. Here we're talking about 9 million words of computer memory. A word is basically the information of 6 letters or 10 numbers.
Mm-hmm.
This is the kind of thing we're talking about. The basic memory of the computer is 65,000 words. So this gives some idea of the scale that we're talking about. And in particular, the supervisor can cause programs to read back and forth from the disk memory. So this is the magnetic disk memory. And we are keeping all the old programs of the different users on the magnetic disk, as well as, the chalk, a little soft.
That's where the supervisor tells the magnetic disk to put something into the active memory over here, or this regular
So
memory.
it's playing a juggling game to some extent, keeping all of the right programs in at the right time. But I still haven't really explained the idea to you.
No, because as far as I know, that computer can still only do one thing at a time.
That's right. And it does just that. It runs one program at a time. And in particular, it proceeds to start one program, operate it for a short burst, just a burst of time. By a burst, I mean maybe, at the moment, we're dealing in about 2 seconds.
Oh, that may not be enough to do the whole program.
No, it may not. And the way now, if it isn't enough, there's a special device we have, which is essentially an alarm clock. I use the term alarm clock. It isn't like the conventional one. What it does is, as soon as the program is run for a certain period of time, the computer is brought back to the supervisor automatically without the user's program saying anything. And the supervisor now can reassign the computer back to another user. Now, this simple round robin is the basic principle of the computer and time sharing. This computer is fast enough to get through all the different users and still maintain a reasonably continuous service at the different consoles.
I see. It just seems as though the computer is handling all these programs simultaneously, but actually it's just going round and round very fast,
yes,
from one to the next.
You can draw several analogies. One nice one is that of, if the supervisor program could be compared to, say, a chess master in a tournament, and the chess master is playing a large number of people all at once. Now, the chess master is usually very fast and clever, and he can essentially analyze the situation rapidly and make his move, and his opponents normally require considerable time to think it over and figure out the implications. And this is the way it is here. The opponents are essentially the people at the consoles who need quite a bit of time to ponder over what the computer has just done for them, or to not be under any pressure, and the computer can be racing back and forth, servicing each one as he needs attention.
Does it give each one of them exactly 2 seconds? I mean, I was just thinking if somebody isn't busy, somebody may have gone out to lunch, what happens to that man's console?
Well, there are two things there. Well, first, we don't bother to serve anyone who doesn't ask for anything.
We
But
skip right over him.
Right, skip right over him. But there's an addition. We have refined it already a little bit. The simple scheme will work, but we can actually refine it a little bit. And what we do is we say the man who hasn't had any computation done for him at all gets the first priority. And so he gets served right away in a short burst of, say, 2 seconds. But if he isn't satisfied with that and he needs more, then we put him in a second priority and we give him lower priority, but when he does run, he gets a longer burst.
Oh, I see.
So this sort of smooths things out and gives the people that need the smallest amount but high priority attention first crack at the computer.
Incidentally, does this save time by not having to re-enter a whole program every time? Let's say you were really going to be using the same set of instructions for a number of problems. Under the batch system, you'd have to put that set of instructions in every time, would you?
That's right.
Every time it came your turn for your problem.
That's right. And this is, of course, would be a very difficult task if we had to do it through the console. So what we really are doing is we're keeping all those old programs. One of the things that are in the disk memory is old programs of each user.
And they're all filed so they don't get mixed up.
That's right. And not getting them mixed up is really the crux of the problem. The disk memories have been available now for about a year or so, but not many people know how to use them because you have to get awfully organized. And the real difficulty is keeping each person separated from the other. And we have had to solve this. In order to solve it, we have one section of the supervisor which has nothing but that responsibility, and it's a major job.
Just to keep things from getting mixed up.
Yes.
Well, could we, say, take an example and actually try this out? Why don't we call ourselves user number 1 and actually go through a process here?
Okay. Well, I can illustrate this best by going. The person would actually type something into the console to the supervisor. The supervisor would then take action on the basis of that. Now, the way the person really initiates anything in this system is he types commands to the supervisor. Mm-hmm. They're about in the order of a few dozen commands. And these are mostly fairly basic instructions, like I want to log into the system or something, or I want to start typing in a program, or I want to run a program, or I want to put something away on the disk. These are rather basic manipulating commands. So in general, the commands are typed to the supervisor, and they cause something to happen from the programs that are on the disk. Now, let me explain just a moment what really happens. What really happens is when a man types a command into the supervisor goes and gets a program out of the disk, which it starts running as, say, U1's program. It brings it in for him and starts to run it as his program. And of course, at that point, he's got a program working for him. It may do something standardized in a standard way for him and then drop out of the picture. Another command, in a particular, one of them is he may want to start an old program, so it'd bring in an old program for him. Now, that's what we saw at the beginning of the program, and I'd like to illustrate that first.
All right. I'd like to see that now that we understand it a little better.
I'm going to type the start command, and that's the first one.
And that will bring our old program, which is already on file, into a position where we can actually use it.
That's right. Now, as soon as I type start, I've actually started my program. So in order to see this clearly, I think we'll have to bring the camera in pretty close.
We can do that, all right. Get a good look at what's being typed out.
I'm moderately familiar with this keyboard. Of course, one gets more and more facile as you get used to it. And this is one of the problems. We have to study the human engineering, too, of people learning to use equipment. Too often the equipment in the past has sort of been designed for other machines, really not for people. But I start out by pushing one button, and then I think I'm off the races. Let's see how this goes. Wow. Now, first, the computer's pausing there. The little pauses are actual hesitations when it's switching from one user to another.
Oh, that wait, for instance, meant that it wasn't ready for you just at that moment.
Well, the wait meant that the supervisor had gotten my command, start,
yes.
And it actually started pulling in that program. If I wanted to type there, I would really be trying to put input into that command program. Now that particular, well, it's actually an old program that I wrote. That particular program that I illustrated on the board doesn't need any input. Mm-hmm. And so it would have been ignored by that if I tried to type. Instead, it wanted to talk to me. And in particular, it says hello. I do square roots and hypotenuses. Please type either root or triangle.
Now, would this be a typical program, or is this a particularly simplified one for our purposes?
This is an extremely simple one, and not at all typical of what we'd use.
That gives us a chance to understand it.
but I have to pick an example which is good for pretty much everyone in a language that everyone understands. But it's illustrative of the technique of man-machine interaction. I think it's very clear that this is the technique that would work in, say, an airline reservation or a small business asking about a payroll problem or something of this sort.
All right, why don't we do a square root then?
Okay, so we type root.
What's it asking?
Please type a number up to 6 digits with decimal point. Want to pick one?
I'm trying to think of one I know the answer to. How about 49?
49? Okay. I don't think. Computer, of course, doesn't have to have the simple ones.
I'd have no way of checking it. Anything more complicated than that.
Now, one thing that's important here is that we could spend considerable time arguing about what the right number to have picked was.
Mm-hmm.
And it really wouldn't have mattered because the computer's working for other people. And we're not losing any of this rather valuable computer time.
Mm-hmm.
Well, I guess the computer's right. It said 7.
Now what does it say? You wish to continue?
Sure. Oh, let's type that.
Please type yes or no.
Well, I think the point here is that we didn't really have to know exactly what to type. See, the program was prepared to check and see if we made what it expected us to assume was the right answer, yes or no. But when we didn't do it, it's able to come back and ask us a question about it.
That's interesting, because this would be one of the problems, I imagine, in the batch system, that it might have taken you 24 hours to find out that you had given the wrong instruction or the wrong answer.
That's all too true.
Doing your part.
That's completely the case, and it's one of the infuriating features of the older way of doing things and what slows down most problem preparation.
That's good.
So let's say what we should have said, I guess. It says, please type either root or triangle, so we're back there again.
All right, well, why don't we do a triangle this time?
Okay.
This is going to give us the hypotenuse of a triangle. I remember earlier it said something about
yes, that's right.
Hypotenuses.
It says, give me 2 sides and I'll give you the hypotenuse. Type up to 6 digits with decimal point. The first side is... Oh, let's pick something a little more difficult than ones we know.
All right, you pick one up.
Okay, let's try. Typing 1.
And the other side?
Let's see, the other side, let me make 12.
All right.
Not sure. I think the answer is going to be 13, but I don't remember for sure. No, it's not 13.
12.04.
Oh,
Well, we better tell them no, we're finished. If you wish to continue, no.
okay.
And we won't make any mistake this time. Tell me one thing. Whoops, this is going to have...
Now, this is the program, at this point, is sort of cleaning up the details.
Let's see. Now, does this... it seems to me that this would actually save a lot of time and that you might wind up with the same problem you had before, the computer loafing.
It's a complicated question about saving or using time. We actually save quite a bit of time in the sense that the person is able to be more selective and be more shrewd in his use of the computer. He doesn't set it on brute force approaches to problems, but actually can probe around and examine some of the smaller answers first before he decides to go ahead. So this saves time. But then there are other factors which make it look the other way. Mm-hmm. And one of them is the fact that we do have a certain amount of overhead switching between one user and another. Now, this is controllable, but and we can keep it, say, down to 10%. But it's a feature. It's one aspect of the system that uses more time. Probably the most frightening part, though, is the fact that we've really made the computer extremely easy to use here. And so it's very clear that in the long run, we're going to increase the need for computer time by a large amount.
Well, we already have increasing needs for a computer. They're being used more and more in all sorts of businesses in science and defense and so on. What would happen if we don't institute such systems as time sharing?
Well, to see that better, I really ought to show you our present operation with a high-speed printer.
That is really printing out a lot of material, isn't it? What is all that?
So? This is output from the computer, from the people using it in the conventional way. Notice the tremendous amount of material that has to come out.
That might all be one problem, one person's problem?
Yes, it's just one person. The reason he has to ask for so much is that he really couldn't anticipate having what he needed to know, so he asked for more than enough.
So what's likely to happen in the future?
Well, just imagine having 10 times as much computer here. We'd have 10 times as much paper. This would leave us with freight cars of paper coming up to the computation center.
Well, by time sharing, for instance, in the demonstration that we did, how much time did we use up on a computer?
Well, the output here, when we logged out, said it only used 18 seconds.
Well, thank you very much, Dr. Covato. Now, next week, we're going to visit the bathyscaphe Trieste, which is in Boston, to help locate the ill-fated submarine Thresher. We're going to meet some of the naval officers who operate the Trieste and learn about some of the scientific experiments that they've conducted in the ocean at depths as much as 7 miles. This is John Fitch, your MIT science reporter. I hope that you'll be with us then.